Good evening, sir. My name is Aman Mohammed Hashim from Chemical Engineering. My user number is 1BM24CH004. Today I'm going to be talking about internal energy and enthalpy, changes for ideal gas, and some numerical problems. So, internal energy, nu, of an ideal gas. Internal energy is basically all the energy stored inside a system, including the energies from every moving molecule. For an ideal gas, this internal energy depends only on temperature, not on pressure or volume. The key equation is delta nu. Mu is equal to NCV delta T. Remember, N is a number of moles, Cv is molar heat capacity at constant volume, and T is temperature. This relation let us calculate how much the internal energy of a gas changes when we heat or cool it. Enthalpy H of an ideal gas. Enthalpy is defined as H is equal to U delta UPV. It's the sum of internal energy plus the energy need to push back against the atmosphere as the gas expands. For ideal gas, H is equal to U plus nRT. The main equation for change is delta H is equal to NCP delta T, where Cp is the molar heat capacity at constant temperature. If we are ever dealing with processes at fixed temperature, this is the formula to use. Now calculating delta U, let's do a practical example. Suppose we heat 2 moles of monoatomic ideal gases from 300 Kelvin to 400 Kelvin at constant volume using Cv is equal to 3 by 2 R and R is equal to 8.314 joule per mole Kelvin. We substitute into delta U is equal to NCV delta T. So delta U is equal to 2 into 3 by 2 into 8.314 into 400 minus 300. That equals 2.49 kilojoule. This straightforward calculation let us predict heat energy. Energy changes from gas heating. Now the next question is calculating delta H. In this example, we have 1.5 moles of a diatomic ideal gases heated from 250 Kelvin to 300 Kelvin at constant pressure. Delta P is equal to 7 by 2 R. R is equal to 8.314 joule per Kelvin mole Kelvin. Plug this into delta H is equal to NCP delta T, where it gives 4.36 kilojoule. We use CP and delta T to get the enthalpy changes from pressure and based heating. Numerical example 3 using gamma. Let Let's use the heat capacity ratio if delta V is equal to 20.8 joule per mole Kelvin and gamma is equal to 1.4 knot. Cp is simply gamma is into Cv, which gives 29.12 joule per mole Kelvin. We check May's relation Cp minus Cv, which gives 8.32 joule per mole Kelvin, were almost exactly 2 hours. This example shows how knowing one property let us calculate others. They are all interlinked. Now, numerical form. Suppose we have, it's a combined question. Suppose we have 3 moles of monoatomic ideal gas. The gamma is equal to 1.67 and the temperature changes from 200 to 500 Kelvin. First, Cv is equal to 3 by 2 R, Cp is equal to 5 by 2 R. Use delta U is equal to Ncb delta T for internal energy change and delta H is equal to Ncp delta T for enthalpy change. You get delta U is equal to 11.22 kilojoule and delta H is equal to 18.71 kilojoule. This spotlights how energy changes differ depending if the process holds volume or pressure constant. Now, key concept summary. Let's summarize the essential relationships. For all processes, delta U is equal to NCV delta T and delta H is equal to Cp delta T. Mass relation is always Cp minus Cv is equal to R. Gamma is equal to Cp by Cv with 1.67 for monoatomic, 1.4 not for diatomic, and 1.33 for polyatomic. For ideal gases, delta U and delta H depends only on temperature, not on the way the process happens. This makes calculation easy and powerful in practical applications. To wrap up, knowing Cv and Cp is fundamental for predicting energy and enthalpy changes in gases. Mass relation and gamma are vital for understanding how gases behave, especially in adiabatic processes. These concepts matters for everything from engine design and havoc systems to weather predictions and rocket science. Mastering this relationship empowers accurate prediction in engineering and science. Thank you. So